Hello and welcome back. In this video, we discuss about the principle of conservation of momentum applicable to a fluid in motion, using a differential approach. The integral form of linear momentum equation, discussed earlier in videos 45 and 46, is useful when we are interested in the global effects of fluid motion such as total thrust from a fluid system, when it is moving through a control volume. A differential approach, which we are discussing in this video, will be useful when we are interested in finding flow properties at a given location of the flow. For example, the differential formulation will result in partial differential equations that can be solved for velocity and density field. Consider a differential fluid element as shown in figure with sides delta x, delta y and delta z. Let the vector function v be the velocity field of the flow. In this equation, u, v, and w are three scalar component functions in three mutually perpendicular directions. Note that u, v, w are functions of space variables x, y, z and time t. Using this vector function we can calculate velocity of a fluid element at given location, at a given instant of time. Let the fluid element under consideration is at x1, y1, z1 and t1. Substituting the coordinates to this function you get the velocity vector at that location. The velocity vector function v has three scalar functions, u, v, w. And these scalar functions are function of space variables x, y, z, and t. The time derivative of velocity vector field will result in acceleration field. Since velocity field has four independent variables x, y, z and t, the time derivative of this vector will result in partial derivatives as indicated. The total acceleration of the fluid particle can be imagined to be a combination of local acceleration and convective acceleration terms. The local acceleration results from time dependence of particle velocity at a given location, while the convective acceleration is the result of velocity variation from one point to another in space. This convective term depends only on space variables and is independent of time. Now we can consider the second law of Newton, applied to a fluid element as shown in figure. The net force acting on the fluid element will be equal to the mass times acceleration of the element. We just discussed about the acceleration term. Now let us discuss about the forces acting on this differential fluid element. For simplicity, consider forces acting only in the x direction. Forces acting in x direction are shear stress in xz plane, shear stress in xy plane, normal stress in yz plane and body forces in x direction. From this we can calculate the net force acting in x direction. Now consider the x component of acceleration as equation A. Equating the x components of force to mass times x components of acceleration, we get equation B. Finally, we assume the fluid as Newtonian and express the stress terms in terms of normal pressure, viscosity and velocity field. This substitution back to equation B will result in the famous Navier-Stokes equations. The three components of Navier-Stokes equation are conservation of linear momentum in x direction, simply call x momentum equation, y momentum equation and z momentum equation. These partial differential equations can be summarized as a single vector notation as equation D. Note that equation D has same format of Newton's second law with mass and acceleration term on one side, and the force terms on the other. These equations are derived for a differential fluid element in the Cartesian coordinate system. Note that, solving these three equations simultaneously with continuity equation, and using appropriate boundary conditions, velocity vector and pressure at a point in the flow field can be found out. Finally, For inviscid flow, the Navier-Stokes equations can be simplified to Euler's equation. From the Navier-Stokes equations, if the viscous terms are removed, it will be Euler's equation. Integration of Euler's equation along a streamline will result in Bernoulli equation. Thank you for listening.